Going. Welcome. This is CS537, if you haven't figured it out. And what we're going to talk about is Project 2. In particular, we're going to talk about Part 2, scheduling in the xv6 kernel. Who started doing that? All two of you. So great. Sounds like it's going to be a fun, what do you have left? A week? See, that sounds like a long time, right? So you're thinking, I'll put it off. That's a bad idea. So in any case, part 2 is the xv6 scheduler, and if we have time at the end, we can take general questions. Sometimes I'll do that. I'll just take general questions from people, and we can look at code and stuff like that. So we'll see. So this is the part where you get to, you've read about, or at least you heard about, schedulers, and maybe you read about them too in the part where we talked about policies for virtualizing the CPU. And now we're going to actually look at a real scheduler and try to make one that's different than the one that exists there. The one that exists inside of xv6 is basically a simple round-robin scheduler. So you have a bunch of processes. You run one for a little while, then you have a timer interrupt, then you run the next, then you run the next, then you run the next. Make sense? That's round-robin. So we're going to do a slightly different one, which is a combination of something you heard about in class, which is the multi-level feedback queue. And of course, you can read about it in this book chapter if you'd like. Yeah, if you click on those links, they actually lead to writing, which you're supposed to eventually read. And then there's this other thing that's going to combine with called a lottery scheduler, which we didn't talk about in class, but takes you like 2 minutes to understand when you read this chapter, or you just look it up online or whatever. So that's the basic idea. There's a few details. You'll have to add a few system calls for this stuff to work. And then there's some suggestions of where to look. And of course there's in fact an xv6 book too, though I tend to think that that's a little bit more detailed than what you need. But you can always look at the latest xv6 book. Now, one problem with that is we're not using the latest version of that kernel because they add stuff that I actually don't want to be in there, but some things are relevant. And of course you can always do what everybody used to do before the age of the internet and the web, which is you could just look at the code. That's the one way to learn about a system. It's like the best documentation is actually the code, and that's particularly true when the code is simple and very cleanly written, which is absolutely true for this xv6 kernel, right? It's very legible C and assembly for the most part. Once in a while it's a little bit ugly, but most of it I think is very well done and therefore makes for a relatively easy reading. So beyond just doing that project, you'll have to make a little graph showing some processes running over time and their priorities changing and so forth. But that shouldn't be too hard once you get the basic functionality working. So read that in some detail. Now let's actually do some stuff. So I'm going to do a few things just so I remember. I wrote down. We're going to, well, build the kernel again. As always, we'll always start with just a fresh kernel. You can always use the one you had for the previous project, but the projects in xv6 land don't build on each other, so you don't have to have the previous functionality, which was a system call, but in general, we're not going to build, so we don't, you don't have that problem of what if I'm doing a bad job the whole time, and does that make me fail the next project? So let's go ahead and start doing that. You grab the kernel from here. You can see in this directory there's actually a README and the xv6. We'll look at the README in a second because one thing we're going to do is we're going to make sure you know how to run the debugger on xv6. How many people have run GDB with xv6? Okay, good, some of you. So I'll make sure everybody knows how to do that. That's really useful, not necessarily even for in-depth debugging, but just sometimes you're trying to figure out like a very simple thing about how the system crashed, and just having a little tiny bit of information from the debugger can go a very long way. That's absolutely true also of your other project, the other half of the project when you're doing a shell. If it's crashing, being able to run GDB and say, oh, this is where it's crashing goes, that's probably 9/10 of figuring out what the problem is. Okay, so we'll start like that. We'll unpack the kernel. We'll go ahead and CD into there. And then, of course, we can make it like that. Of course, we can run it. We can run it in two different ways. We can just run it graphically, or we can run it without X, which is not graphical. So I'll do that. And of course, this works as you expect. Not too exciting. And then down here, you can do things like there's no proper halting. So you can do things like kill that process is one way you can get rid of that and then get out of there, or there are other ways too. So first thing, before I get into the scheduler, I just wanted to show everybody how to run the GDB part of, or run xv6 in GDB rather. So not surprisingly, the README tells you how. And you have to find the right README, which is the README that we provide. There's a README inside of the xv6 directory that's just talking about xv6 from the authors of xv6. That's not as relevant for running the debugger here. So anyway, you can see here, this is about xv6, more information there, whatever. This is what we've already done, tarring it. You don't really need to copy it. You already know how to build it. You already know how to run it. And then what it talks about down here is how to run it in the debugger. It's actually fairly straightforward, but there's a slight catch that some of you might have run into. The most important thing is to have two terminals open, both in the xv6 directory that you just unpacked, right? So have two terminals open in that same directory. And then in one of them you type this, make qemu-gdb. And then the other one, that's basically going to boot up everything, but then it's going to wait for a GDB process to connect to it. And we're going to show, and then you do that from the other window. Okay, and then you can do all sorts of crazy things like set breakpoints in the kernel and continue, and then run until that breakpoint is triggered. All sorts of fun stuff like that. So you can do all the things you'd expect to do in a debugger, and it's good to spend time learning how to use that tool, just generally for your own programming skills. In any case, you can always read more about GDB, and when somebody points you to a link like this, that means there's a lot of reading you could do about GDB. You could spend many hours reading about GDB. So instead, probably the way to do it is do small things at first and then slowly learn useful things. And we'll come back to this a few times throughout the course as needed to understand different parts of the xv6 kernel. So let's go ahead and do that. Maybe I'll do the no-x version. I think there's a no-x version as well. No, it's not like that. It's no-x-gdb probably. Okay, so that kind of hangs there. It looks like it's doing nothing. Now there's one tricky thing, which isn't really that tricky, but you have to add a line in your GDB init, .gdb, your top level. This is like tilde means you as a user, and then slash means in your top level directory, and then .gdb init is just a file there, so you can do an ls on it. You have to make sure that there's a line in there that lets you use the local .gdb init. So that's in that file .gdb init. You have to add this add auto load safe path, and then whatever the path is that you're in right now. In fact, I don't have the right path right now, so I suspect it'll complain. Let's see if that's true. You can see it's not doing very much at all, which is no good. Well, let's see, is it working? No, it's not working. So let me go ahead and see what directory I'm in, whatever. This is actually most of a full path. Let's see if this works, and of course if this doesn't work, then it's a very bad demo. Worse things have happened inside of class before. Oh, am I in the wrong directory? Sorry, I didn't even look. Yes, I'm in the wrong directory. So let me erase this so I don't do anything. So you can see how easy it is, even for an expert. Sorry, I'm supposedly an expert in getting that wrong. So anyway, let me run GDB, and you can see it's actually complaining about that path. It's saying, warning, they detected, .gdb init, which you need to, so the GDB knows how to connect to that thing we started up here. But it's been declined because your auto load safe path does not include this path. So in fact, it tells you exactly what to add to your .gdb init file so that this works. So a lot of times, surprisingly, when a computer is complaining at you, you should actually read it and then actually do what it says if it's telling you something reasonable. Of course, sometimes it doesn't. It says like, debit $1,000 from your bank account. Okay, no, maybe not. But in this case, we actually are going to follow its advice, and we're going to go ahead and do that. And let me make sure that looks right. Sorry. You can see the screen is too big, so I'm going to make it smaller. Sorry. That looks kind of right. It's kind of a long path. I can make it actually a shorter path, but not that it matters to you. And then we'll try again and see if it complains. And then you can see here it actually, something different happened. It said, oh, it kind of understood where the kernel is and some stuff like that. So that's a good sign. And then we can continue it with continue or just C or continue, and you can see what happens. Finally, the kernel boots. Okay, so for those of you who did that, congratulations. For those of you who haven't, it's useful, and then this runs like normal. But you can do all sorts of things. You can control C over in GDB again. Control C kind of gives back, pauses everything again. Then you can do things like set breakpoints at different places. For example, at maybe like the switch routine, which we'll look at later. And then you can continue. And up here you can do things then. And you can see, oh, look, we ran into a switch, which is actually a context switch, which we'll look at in some detail in a little bit. So you can do all sorts of fun things like that. And we'll get back into that in a second. Does that make sense? Sound like something you can do? You'll read warnings when they complain, when things don't work, and you'll read it and you'll follow instructions. Good. Okay. Okay, so let's look a little bit. What we're going to try to understand here is we're going to try to understand the scheduler a little bit. So we're just going to trace through how that works. It looks simple. It's in some ways deceiving how simple it looks. And so we're going to make sure that you're not deceived by that, because you're going to be modifying the scheduler, and it's actually easy to do that in kind of simple but wrong ways. And it still shouldn't be that hard to do what we're trying to do, but you should understand the control flow. And it's different than what it looks like because of the way the kernel context switches. Okay, so let's look at the kernel. And we'll start in, well, why don't we start in main? So main is what, you know, all the stuff that happens when we're booting up. We've talked about pieces of it. For example, setting up things like trap vectors, all very standard. There's a lot of things that get initialized when a system boots up, and in a real system, not just xv6, you'd have a much longer boot sequence that does a lot more initialization of everything in the system. Here it's a relatively minimal one to deal with some interrupt controllers, set up some OS structures, and then eventually do things like boot the, it's a multi-processor system, so it starts up other processors as well. Most of the initialization actually occurs on just a single processor in xv6, and then other processors, kind of a lighter weight setup, and gets going. But then what happens at, whether you're the main processor or any of the other processors, what happens at the end are a couple things. One is this user init routine is called. This is not something you'll have to deal with at all, but it's useful to understand how Unix systems boot. When they boot, eventually they want to run a user process. In fact, what's the first user process that you see when you boot up xv6? The shell, right? There's a shell running, but that's not the first user process, because you can imagine why that isn't. So they actually, most Unix systems create a process called init, which is the initial process. That one's created differently than every other process. How do we generally create processes? Talked about this last week. How do we, in a Unix system, how do we create a process? We call fork, right? So you call fork. What does fork do? It creates a child process that is copy of something that's already running. So that means you have a problem that's really good for everybody except the first process, right? The first process you can't create as a copy of something because there is nothing to copy. So it's always a pain to create that first process. And if you want to look at that, at some point we'll look at that in a little bit more detail perhaps. But user init creates that first init process. And eventually that runs and creates the shell, which is what is running then when you're log into the, basically when the system comes up to you. First init runs, it forks and creates the shell, and then the shell forks and execs, and then the shell starts running, and then you can type. But after that, you can see the last thing. This looks like the end of main and the end of the OS. It's of course not. But what the OS does on each processor is call into a routine called scheduler. This is where you'll be spending a lot of time, is understanding that little code sequence inside of scheduler. It's not super complicated, but it's, like I said, the control flow is going to be a little bit non-standard, so we're going to walk through it. Okay? And you can see scheduler here, and then probably in boot others, I suspect the same thing, boot others, which eventually calls here, mp main, which calls scheduler. Okay? So basically, every CPU that's booting inside of this xv6 multiprocessor kernel will eventually call into the scheduler, and you can see that's not going to return. That's just going to call into the scheduler and then run things until the system is shut down. The scheduler is inside of proc.c, so that's where you'll be spending some time looking. There's a lot of code in there. There's some initialization things. Now, we haven't really talked about locking, so I'm just going to warn you about locking. We're going to talk in great detail about this when we talk about concurrency, which is coming up sometime, next week or maybe the week after, depending on how we get through the rest of the virtualization discussion. But you'll see a lot of these acquire and release statements around certain sensitive pieces of code. Like anytime you're accessing the process table, which we'll look at in a little bit detail today, you can see they're sure to they're holding this lock is what it's called. And that's to make sure that when multiple CPUs, or even something on the time, sometimes the same CPU, but you can think of it as multiple CPUs are entering the same piece of code, that when they update data, the right thing happens. We talked a little bit about that on the very first day, if you remember, way back to that, when you were looking forward to the class. In any case, this is what's going on here, and you have to be a little bit cognizant of it, though not too much in this assignment. So anyway, we're going to skip that piece. We're going to skip that piece. You can see this is some of the code that actually runs when they're setting up the first user process. That's rather ugly code that you don't want to look at. I'm going to go down further. You can see there's fork and its implementation. Actually, I think the next or the fourth project we'll be looking at fork in great detail. I think the fourth project, and wait. You can see all the, if you're interested in how those system calls work, fork, exec, wait, you can just look in proc.c. But eventually you get to this scheduler, and this is again called by every CPU after booting and getting ready to run. They just call into the scheduler and basically just stay inside of here. And you can see this right away. What does this C construct mean? For parentheses, semicolon, semicolon. What does that mean? Yeah, it's forever essentially. It never terminates, right? There's no condition under which it terminates. Okay, so we're going to ignore some stuff like this about enabling interrupts, but you can imagine why we need to enable interrupts at that point. And again, we have this kind of locking stuff going on, which we're going to kind of ignore. But you can think of it as anytime you're messing with this process table, what you're going to be doing is you need to be sure that you have previously acquired this lock. If you don't, bad things are going to happen, and you're going to have a very hard time debugging it. Of course, why would you? They already do that correctly, so you probably should just borrow what they're doing here. So let's look at this loop of the scheduler. It's not very big at all. Let's see if I can make this page any bigger. So basically, here's the end of the loop, that forever loop, right? Yeah, you can see down here, Emacs is telling me it matches the 4 here. So that's the forever loop. And then let's make this a little bit squished together so we can read the whole thing. But that's it. That's kind of the scheduler code right there, right? Which is remarkably simple. I mean, you shouldn't expect the round-robin scheduler to be that complicated, but it's nice to see that it's actually a very constrained, concise piece of code. So let's see what it's doing. What it's doing here is it starts with P. You can see P is a pointer to a struct proc. So let's understand what that is a little bit before we get into it. You can see this is the per process state that xv6 manages. I suppose I should have asked, can everybody read this? But it's way too late for that now. So if you can't, move forward. There are seats near the front. And we talked about this a little bit in class, right? For every process that's running, every time you run a program, the kernel is going to track that program in some way. And in xv6, it just has this really simple array of process table entries or proc structures. And those proc structures then just tell you something about each process in the system. And a lot of times these slots will be marked unused because they're unused. But depending on how many programs you're running at a given time, it'll either be running or ready to run, which means they could be run, but the scheduler's chosen not to run them, or so runnable, or running, or sleeping, like waiting on an I/O. Zombie is the state that you go into when you've exited, but you're waiting for your parent to wait for you. so you're dead essentially, but not yet reaped. And then embryo is a state that the process is in when it's being created, and you'll see that at some point later in the semester. And then you can see unused is a state to mark this entry in the process array or process list, as there is no process using that slot right now. Does that make sense? Okay, so then there's a bunch of stuff in here, not all of which is very relevant to us, but you could imagine one thing you're going to keep inside of this process structure is any additional scheduler state you need. If you need to do some fancy scheduling stuff, like I'm trying to build a lottery scheduler, and a lottery schedule needs to know how many tickets there are that process has, you can imagine you'll create something in here that says like, oh, the number of tickets that this process has. Or I'm trying to keep track of something for my multi-level feedback queue. So whatever that is, you would probably create it inside of here, because that's a pretty natural thing to look inside of to know something about this process. Does that make sense? That's like hint number one. Okay, I don't know how much I have to point these things out, perhaps somewhat. And there's a few other things like the process ID. This is the state, right? This is, which is up here, the whether it's runnable or whatever. This is the kernel stack. We talked about how each process, remember we tend to think of processes as code and like a user stack and a heap, right? Those are all user constructs that your program can see, but each process in xv6 and in other kernels has a kernel stack, and that's used for when we, for example, trap into the kernel and save register state, we save it onto our own kernel stack, and that's where we restore that state from as well. So that's just for your knowledge. We now know about page tables. xv6 is a page system. It uses a multi-level page table if you've been following along in class, which you should be. And that's defined by the x86 hardware, and that's what they use. And this points to, not surprisingly, the root of that multi-level page table, or the page directory, if that makes sense. So we'll see that in the next project in more detail. This is the trap frame. We talked about it, and this context is kind of interesting. We're going to look at that in a moment. But in fact, it's right here. You can see it's just a structure that are basically where saved registers go for kernel context switches. It's nicely commented here. What we're going to do is we're going to have to try to follow this control flow, but sometimes a process is running and then a timer interrupt happens, so we save our state onto our kernel stack. Then the kernel runs, and the kernel is going to decide to switch to another process, right? So it's going to switch to another process. Now that other process in general is essentially is sitting parked in the kernel, having suffered a previous interrupt, for example, and had its state saved on its kernel stack. So what we're going to be doing when we do a context switch inside the kernel is basically switching from one kernel stack running on process A's kernel stack to running on process B's kernel stack. And when we're saving the state of a particular running process, we're going to save it inside of this context structure. So it's a little bit complicated. We'll discuss that again in a moment, or it's not complicated. If it's not, by the way, if I ever say that and you find it very easy, you should just feel good about yourself. And then you can, after class, you can like call your parents or whatever and tell them, professor said something was hard, but for me it was easy. I think things are going great, whatever. So if you're all feeling that way, then I'm probably doing a bad job. So anyway, there's a few other things like we'll get to eventually here, like open files, for example. So when you open a file, the kernel keeps track of that. There's a general, so it says which open files and which file descriptor, things like that, which directory you're in, and then a name for debugging, like, oh, this is the shell or whatever. Okay, so any questions about that? That makes sense, kind of? Proc structure. What you should absolutely have in your head, when I create a process, I need to find a proc structure, and that proc structure is going to be in the process table, and we're going to use that to track things about the state of this process. Okay, let's go back here into our scheduler. Let me poke down again so you can see the whole thing. So you can see here, after grabbing this lock, you can see a very simple thing here, which is, in general, what are we doing here? What is that loop doing? Just the first part. I mean, we don't have to understand the whole thing. You can stare at it for a second, though. So we're starting with we're basically, what this loop is doing is simply looking through the proc structures, you know, you can think of it as from 0 or the start of the table to the number of processes in the system, max. So this is not even a process list, right? It's an array. And if you have more than, you know, what nproc is defined to be something, let's figure out what it's defined to be. You can see it's 64. If you try to create more than 64 processes, something won't work. That's just how xv6 is. It's very simple. A lot of early Unix kernels use very fixed, simple structures like this, like arrays. More modern systems will use more complex and more flexible data structures, like, for example, a linked list or something even more sophisticated than that. But here we just have an array, and we're just going to go look through it. And basically what we're looking to do is to pick a process to run and then start running it. Okay, so this is where the magic occurs. The kernel is running. It actually, when it booted, remember we saw it created this init process, right? So there's one process that's created, and it's a runnable process, but it's not yet running. And then what the kernel needs to do is to basically run it. So it needs to find a process that's runnable and then somehow get it running. Okay? So you can see what it does here. It says if the p state is not runnable, what am I going to do? Continue. What does that mean in C world? This is something you should all be understanding probably at this point. What does continue do here? Yeah, basically just skips the rest of this loop and just goes right back to the next, essentially the next iteration of the loop. So if this entry in the array is not runnable, I'm going to go to the next one looking for something that is runnable. I'm eventually going to hopefully find something that's runnable, otherwise we're going to have a problem. But that's okay, that happens too. And then we're going to switch to it. And then you can see that at that point actually there's some code that has to run somewhere else that releases this p-table lock. Because if we were holding the p-table lock and then we switched and started running a user process, we could get into all sorts of bad things happening in the kernel. But let's not worry about that right now. It then sets proc. You can think of proc is basically just saying, you know, this is like the currently running thing. It's called proc. And then this is some address space stuff. Switch UVM. We can look at that code, but we don't really need to understand that code right now. If you look at it, it's in vm.c, and basically what it's doing is some low-level stuff to set up the page table, like this page directory. Remember when we talked about in class, like when we talked about when you're doing a context switch and you're switching between address spaces, you have to switch that page table base register, right? To say we used to be in this process and now we're running in this process's address space. That's like exactly going on here. The else load CR3, this is a C wrapper around a hardware instruction, and it's saying use this page directory of this current process. So this is just setting up the virtual memory address space to be using this process's address space. Nothing too exciting here. We can ignore that for now. You can notice it's changing the state of the process. It used to be runnable, right? But by virtue of having fallen through here, that must be runnable. Now it's going to be the running process, right? So everybody's runnable at the beginning, you can think of it that way, but then there's only one that's running. And then we do this very interesting thing, which is we call switch. So this, if you're looking at this and you just understand C but you don't understand operating systems, then you'll say, well, you call switch, then you call this, then you call this, and then you go back to the top of the loop and who knows what's happening. But what really happens here is a very critical thing, and we'll look at this code in a second, is we're going to switch from, right now we're running on the scheduler's kernel stack. The scheduler has its own kernel stack. That's generally saved inside of this structure, which is it's actually one per CPU, and the CPU arrow scheduler is this kernel's stack. What this switch routine is going to do is save the current, like the registers right now that are in this code onto this structure, and then essentially restore the process that's about to run's registers. And in doing so, it's going to actually switch to that process's kernel stack, which is, remember that process, who knows what it is. It was probably like trapped in the kernel on a timer interrupt or something like that. So suddenly we're going to be running in a completely different context. We're going to be running as if like we're in the context of that process that we're switching to, which might do something like return from trap and start executing. So it's a very weird transition, and we're going to try to make a little bit more sense of it than I just explained. But what it means is generally then a lot of stuff happens. When you call switch, suddenly you're going to be running in some other, you can think of it as running some other part of the kernel because you've changed all the registers to be somewhere else on a different kernel stack, running in some different part of the world. And then that's going to, in general, going to be something that returns from a trap and starts executing that user process. Then when that user process has been running for some time, eventually a timer interrupt is going to go off. That's going to find its way back into this code and then continue here. And we'll see how that happens as well. Does that roughly make sense? Questions about that? Let that sit for a second. Why don't you think about it for a second, see if you have a question. Yeah.
Does that mean like when you run that line, the following program is vanished?
Yeah, so the question, if you couldn't hear it, was like, does that mean the stuff following this kind of vanishes? It's not really. What it's doing is we're essentially saving the registers so that at some point if somebody restores those registers in that kernel stack, we'll essentially resume running right as if we were kind of returning from that switch. So it basically puts it on hold, and then you can think of what later we'll be able to continue it essentially. So we're putting it on hold, we're saving enough state so we know where we were when we were running the scheduler, then we start running inside the context of another process. It does some stuff, eventually traps back in the kernel, and then if it switches back to the scheduler kernel stack, it'll just resume right here and then come back around the loop again. So it's a very weird, it's the strangest for loop you'll ever look at, right? Usually you look at a for loop, you'll say just execute a bunch of stuff and keep doing it, but it's going to do it in between while running user programs, right? And then when they're running, obviously this code is just suspended. Yeah.
So if you call scheduler though, it'll start at the top again and just obliterate old data.
Yeah, you shouldn't call scheduler again. Yeah, no, I don't think so. Yeah. Yeah, this is a one-time, you should enter it, and then it just stays inside of it. Okay, so let's understand a little bit about that. I think there's two pieces we can look at. We can of course look at the switch code. That's only going to make some sense to you if you understand x86 assembly. And then we also need to look a little bit at what happens on a trap, how we kind of restore ourselves and so forth, and the control flow there. So let me look at, let's look at the switch code, sure. And you can see, unfortunately, it's not switch.c, it's switch.S, which means it's assembly code. So we have to understand that a little bit. But it's really not too bad. It's really, that's it right there. And you can see what it does is it basically uses push takes a register and puts it on the kernel, the current stack that you're pointing to. And then what it does here is it switches stacks, and it also ends up jumping to a different part of the code through this return and restoring some new registers. So we basically just end up switching context completely and jumping to a completely different part of the code. And you can study this on your own if you're interested, or walk through it. In fact, I'll show you in a minute how to step through it if you're really fascinated by these types of things. But for now, we will not make too much sense of it. But it'll return. When it returns, it's going to return because you switch stacks, right? Usually, think about it like this. Usually when you make a procedure call, or a function call rather, either one, same thing, you jump in, you do some work, and then when you hit return on x86, what happens? Well, does anybody know what happens when you hit the return instruction on x86? How does it know where to go? Yeah, when you call into a function, you're pushing the return address onto the stack that you're running on. And then when you return from that function, it pops it off and jumps to that address. So if you jump into a routine and then you execute some instructions and then you switch stacks, when you return, you're not going to return where you were. You're going to return somewhere else altogether, wherever that stack tells you to return to, if that makes sense. So it's confusing, right? And it should be confusing because it's an OS, and that's why we have a class about it. So if it weren't confusing, then it would be called, I don't know. Be called something else. Yeah. You have a question or scratching your head? All right. This looks like a question to me. So, and for those of you listening online, it was very exciting. So, Anyway, let me look at something else. I want to look at trap.c so you have an idea of how this all... We looked at trap before. Remember, you looked at this part of the code probably in some detail, or you looked at syscall. But remember, when a trap, basically any trap or interrupt that occurs in xv6, they're all directed to this trap routine. So a system call happens, and it says, oh, is this a system call? Yes. But we also have this timer interrupt. The timer interrupt is pretty critical for implementing our scheduler. We're not implementing a round-robin schedule, or sorry, a cooperative scheduler. We're implementing a schedule that relies on a timer interrupt to go off so that the OS can regain control, stuff we talked about a few weeks ago in class, and then decide maybe to run something else. Or decide to run the same thing. That'd be fine too, depending on what the scheduling policy is. So that timer interrupt will actually call this trap routine, but it'll be handled down here. You can see it says here, oh, if this is a timer interrupt, do some stuff. And I'm going to mostly ignore this piece and then actually let the programmable interrupt controller know that the interrupt, you're at an end of interrupt. That's stuff we don't have to pay attention to. And if you're not careful looking at this code, you'll think this is all that happens on a timer interrupt, and you'll be confused how that ever leads to a scheduler change. Where you have to look is there's all these different interrupts that get handled here, like the keyboard and IDE with disks and things like that. And maybe we'll look at that later. But eventually, under all of that is the code that is important to you, which is if there's a process running, and you can see that proc global variable is useful for that, and that the state of that is running, and the trap number is a timer interrupt, then do this thing called yield. Okay, so you were running along, you're a user process, a timer interrupt goes off, it directs to this trap code, and we talked a little bit about the details of how we get in there with the trap vectors and kernel state, register state getting pushed, the user program getting pushed onto the kernel stack. If the timer interrupt occurs while you're running, eventually it says, let's call yield. And yield means give up the CPU, essentially yield control back to the scheduler. And we're going to see how that happens in a second. Does that make sense? And by the way, this kernel, you have to, it's one of these things, any code base like this, it takes some time to get used to it. Like, you have to kind of poke around it and try changing little things. When you think you understand something, try changing it. Then you'll know if you really understood it, right? It's very easy to change, to think you understand it, hear about it, and then you go to try to do it, and what happens is the kernel panics. Right? Very easy to do that. I do that too, It's all the times you'll have some assumption, there'll be some corner case you miss, and then the kernel panics because you're completely wrong. So don't be worried about it. That's what's very nice about this environment. You can get used to panicking the kernel and not feeling like badly about yourself. So let's go look in proc.c where we can see the how we yield exactly. And what yield does, remember we were running in the context of a user program. It trapped into the kernel. The kernel stack that we're running on right then is the kernel stack of that running process. First thing it does is acquire this process table block, and then it changes its state. You can imagine what its state was before we entered yield. What was it? Running, right? It was running. It was running because it got interrupted. It was running. Now we're going to change it to runnable, no longer running. And then we're going to call sked. Okay, so let's look at sked. All this activity is in proc.c, so you don't have to look around a lot of different parts of the kernel. You can see it here. And what we're going to do here, really it's a bunch of stuff you can ignore, and then the same switch routine. So we saw the switch before, the arguments were kind of in the opposite order. It was saving inside of the scheduler, it was saving the current state to this structure, and then restoring this some processes context. And here we're doing the opposite. We're saying save our registers now into this context structure, and then basically switch kernel stacks and return into the scheduler, if that makes sense. So we're going to be resuming the scheduler and where are we going to be resuming it? Well, generally we're going to be resuming it right after this switch statement, because that's where it saved its state, right? It kind of popped in there. Now we're going to essentially continue that. Before we save some state, now we're going to continue running the scheduler after having run a job for some time. So you can see it's a more complicated control flow than you think, and you just have to be cognizant of that. You can almost do the project while being completely unaware of this. but in general, that's not the case. Now I'm getting a phone call, which I never get, and I'm going to ignore it. It's not. I have to check it because it could be my children, and then I would have to answer it. So that would also be awkward. Dad, can I have a sandwich? Okay, I'm in class. So that hasn't happened yet, but I suppose it could happen. Any case, that's kind of the back and forth. Okay, if you can look at it, there's a scheduler code. Then there's the timer interrupt forces a yield, which gets us back in here. But you can also think what that means. If you looked at the state of a running process that got stopped, when we resume it, what's going to happen? Like, how do we start running again? Let's say I'm running along. Let me rephrase that. I'm running along. I'm a process A. A timer interrupt goes off. I'm forced into the kernel. I call yield. Okay, I call yield. The scheduler runs again, decides to run somebody else. Let's forget about it. Eventually, this loop comes back around, and lo and behold, it picks me again to run. Process A comes down here, and it executes a switch. It switches back to me. Where am I going to run? Where am I going to run from that point on? Yeah.
The same instruction you interrupted.
Yeah, right. But how are we going to get there? That's exactly right. We're going to eventually get back to we're going to run the instruction after that. How are we going to get there? What did we call? Like, we called yield, which called what? Sched, right? Which is right here, which called switch. So it's just going to essentially resume right here, return from, sorry if you can't see it, sched, which is going to return from yield, which is going to be inside of the trap routine, which is going to eventually return from trap and so forth. So all this control flow is actually not so terrible to understand, but you just have to kind of make a little bit of sense of it. Okay, so let's look at the scheduler again. So that's that piece. Let's start putting some things in there so we can see, something interesting. Let's say, have you used cprintf yet? It's a console printf. This is a useful, if you're not like, hey, I don't want to use a debugger, that requires some work. There's our old most basic debugger. It's called the printf debugger. In xv6, it's called cprintf. So we could say about to run something, and we could say, let's print out its PID, and let's go ahead and print out its name too. I think there's a name flag, and like this. So we can go ahead and print that and just see, what's exciting about that. Probably not that much. But it's good to know how to do that, and let's just run it like this. And you can see what happened here. The initial thing that runs is a init, right? It's a init code, which eventually was called the init. And then it says starting sh. That's what init prints out, actually, just in the code. And then it says starting sh, and then it says, now you can see it's PID2, and it goes init. But then I'm printing out the name here. It says init, 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 and then it says sh. Why is that? Yeah, this is like fork. Init forks itself, right? I try not to use that formulation. Init calls fork. I've gotten into trouble with that more than once. It's like you call fork to create a child, right? So it's quite vulgar, actually. So you have to be careful with that. That's in class, and now I'm not going to be able to focus because I'm really immature. In any case, init, you can see here, init called fork, and init therefore created a copy of itself. So when we print out its name and it's getting run, it's just saying that's init, but it's process 2. But eventually it calls it exec, which overlays init with the sh, the shell's image, and therefore when it prints out it's about to run it, it runs sh. Okay, so you can kind of see that. It's cool.
So why, like, there's timer interrupts going off right now, so why don't we keep saying, like, about the shell or whatever?
Yeah, right now what's happened is the shell has, that's a great question. The shell has gone into, the question is why aren't we seeing a lot more printouts? And, well, does anybody have a guess, actually? Why not? Why isn't it saying it's running the shell over and over again? It looks like the shell's running. Is the shell running there? Yeah, it's waiting for input, right? So it's actually sleeping. It's waiting for the user to type something. So nothing is running right now. Everything is basically waiting on something else, and therefore the scheduler isn't doing anything. It's just, you could think of it as in that loop looking for something that's runnable and not finding anything. So then when we type something, all sorts of fun stuff happens. And you can scroll back through there and see what's going on. You know, we typed ls, and you can see it creates again a copy of itself, right? By calling fork, which is PID3. Eventually, that's going to become ls, and that's still, of course, same PID after calling exec, and then of course it finally does run it, and so forth. And then you can see, and then whatever happens. Then eventually sh runs again when it waits for that to complete. And we can do that again and again because it's pretty exciting. Okay, so that makes sense. Okay, we can add a little bit more diagnostic stuff here. How are we doing on time? Oh my gosh, we're running out of time. So that's okay. We're getting a sense of that. I wanted to add one more thing. You can, of course, do some more interesting things, like you can add your own user programs to test some stuff. Let me write a little program that does almost nothing, but it could be very useful for you, which is called spin, which is going to take a single argument. And if that argument is basically going to be how many times to spin in this loop, let's go ahead and do this. Let me just say something like this. Don't want the compiler to remove the loop altogether, so maybe I'll do something like this. But basically, it's just going to spin in this loop for however many times. I'm going to pass it an argument. Oh, not this. A to I argv1. So I'm going to take the first argument, I'm going to turn it into an integer, which is what a to I does, and then I'm just going to do this loop that many times. Okay? So the longer I give it, the longer it'll run, and the more we'll get to see the scheduler doing something, if that makes sense. And of course we have to add that to our makefile in the user directory. So this is just a user program that we're adding to xv6. Make sense? Simple program, spin. Let's see if I built it right. Looks good. Let's go ahead and run it like this, sure. So I'll do this spin like, you know, 1,000, I don't know, let's make it for a while. It probably has to run for a while for this to make any sense. And let's run 2 instances of it. And you can see here I'm using the ampersand because I'm going to run a background process. So I want both of these to launch and both of these processes to be active in the system at the same time, and the scheduler to switch back and forth between them. And then they're each going to run for some amount of time. Okay? Some number of loops. Let's see if this works. And you can see here, it looks like one of them stopped. I don't know why it keeps going like that. Seems to have run one a lot more than the other, which is odd. Oh, that's strange. I have no idea what it's doing right now. But you can see at least here, when it was working, what it was doing. I don't know what I did that would break that. Oh, did I run that one just many long? That's probably what I did. I like that as a guess. In any case, you can see what it's doing here between 5 and 6 is just alternating between them. So it's just a strict round-robin scheduler running for one tick at a time and always just switching back and forth between them. Obviously, your scheduler is going to have to do something more complicated than that. So that's the basic idea. And now I'm just going to kill this because it's not that fun to wait for. And there it is. Okay, it did finally exit. And you can see, because the way the background processes work. Here's a little quiz for you. Try to find where it prints zombie in here or why it's printing that. That's your task for the week. So that's about time. We have time for a question or two. Otherwise, I just have office hours after this. So if you're interested, find me in office hours. All right. Good luck with the scheduler and the other parts of the project.
This discussion next week, is that going to like stick with this?
I don't know. I haven't figured it out. I figured that out like next week.
Okay.
Yeah. Good question.